While the European Space Agency keeps its eyes on its Huygens probe exploring Titan, and the Americans prepare to hammer a comet with deep impact, the Canadian space program continues along with missions of a more modest nature. But don't let that modesty fool you. With clever engineering and a steely focus on the mission, a new Canadian satellite is producing solid scientific results on the kind of budget that NASA uses for coffee and mission control. A paltry $42 million. The Canadian Space Agency's SciSat Ozone Observatory was launched a year and a half ago and has been collecting valuable data that will shortly be released on the state of the Arctic atmosphere. Dr. Peter Bernath, a professor of chemistry at the University of Waterloo, is the mission scientist for the Atmospheric Chemistry Experiment, or ACE, the current project on the SciSat satellite. Dr. Bernath, welcome to Quirks and Quarks.
Thank you, Bob.
First of all, tell me about this satellite.
Well, it's great. It's a small science satellite. It's about 1 meter across. It's sitting there looking at the sun, and every time the sun rises and the sun sets through the atmosphere, we record the absorption of the atmosphere.
Wait a minute. You said it's 1 meter across?
That's right.
That's the size of a suitcase.
That's right. A large suitcase, a trunk, maybe.
How was it put up into space?
Well, it was launched by NASA on a Pegasus XL, a small rocket that was dropped from the bottom of a jumbo jet. In fact, it was a retired Air Canada jumbo jet.
Really? So what, they put the rocket on the bottom of the jet,
right,
fly the jet up, and then drop it?
They go up to 40,000 feet, go out over the Pacific Ocean, and drop it.
Well, how does this satellite actually do its work?
Well, the satellite is quite simple. We're using the sun as a source of light, like a light bulb. And during a sunrise and a sunset, the light from the sun passes through the Earth's atmosphere and is absorbed or attenuated. And this type of measurement can get you both the concentration of the molecules in the atmosphere as well as their identity. And the amount of absorption of sunlight gives you the concentration. And the particular color or wavelength of the absorption, that's what tells you what the chemical is. So each molecule has its own characteristic fingerprint, its own characteristic color of absorption. And it is that pattern of absorption that allows you to identify the chemicals.
So, in other words, you're watching the sun set, and the light, the color of the sunlight changes as it goes through the atmosphere.
That's correct.
And you can tell the chemistry of the atmosphere because of that.
That's right. So we can deduce the concentration of the molecules and particles in the atmosphere, and we can also deduce their identity from the different colors that are absorbed.
How accurate is it?
Well, we think it's fabulously accurate. In fact, I would say it's perhaps the most accurate satellite up there now because we have a fabulous precision because we're using the sun as a source. That gives us a very high performance because the sun is very bright.
What types of molecules are you seeing?
Well, that's another real advantage. We're looking at 35 molecules, ozone, nitric acid, all the molecules that create ozone, all the molecules that destroy ozone, hydrochloric acid, and so on.
What's the advantage of doing it this way compared to measuring these chemicals from the ground or sending up balloons?
The main reason is global coverage. On the ground and from balloons, you get a great picture, one spot. But atmospheric science is a global affair. What you do affects your neighbors, and you need to get a global perspective to get an overall understanding of what's taking place. And so the big advantage and worth the cost is this global perspective that's necessary to understand these global problems.
Well, what kind of results have you seen so far?
Oh, so far, lots of great things. One thing we've seen is high in the atmosphere in the Arctic and in the Antarctic, they have something called noctilucent clouds. These are clouds that appear in the summer, and they're thought to be ice particles, very high, 80 kilometers, but no one has actually ever recorded a spectrum of them. So people just speculate that they're ice clouds. And we've got the first spectra. They are indeed very small 50 nanometer ice particles. Similarly, for water, we're in the stratosphere, water vapor has been increasing at about 1% per year for the last 50 years. And this has real effects because this causes chemistry, it causes more particles to form, and has climate change implications because water vapor is a greenhouse gas. In fact, water vapor is the most important greenhouse gas, not CO2. And what we have found, we've discovered that these increases in water vapor in the stratosphere have ceased. So nobody knew why they're increasing, and nobody knows why now they've stopped. So we've got measurements on long-term trends for climate change.
Wow. What about the situation with ozone?
Well, we are just starting our analysis on the ozone. We're coming into another Arctic ozone campaign. That is to make measurements both on the ground. We're sending people up to Eureka in the high Arctic to measure on the ground, and we'll measure from orbit at the same time. And these kinds of measurements are spectacular.
Well, based on what you've seen so far, do you have any indication that the ozone problem is getting any better or worse or the same?
No, there's no indication. So what we have indication, though, is that the Montreal Protocol is working, and hydrochloric acid is now stable and started to decline. HF is no longer increasing, this hydrofluoric acid. These are the molecules that come from the fluorochlorocarbons that are destroying ozone. And it's clear that these chemicals have peaked or started to even decline. And ultimately, ozone will be back in 50 years, but so far no evidence from anybody's measurements. Of course, lots of people are measuring ozone, and nobody has any evidence of the restoration of the ozone layer yet.
But at least the source of the problem is diminishing.
The source of the problem is diminishing. It just hasn't trickled through, I guess, to the ozone yet.
Now, I understand that NASA is using your results to calibrate their own satellite. Can you tell me about that?
Oh, yeah. They've launched a $1 billion satellite called Aura, and it is a fabulous satellite. It's got lots of instruments. And the beauty of our technique is it's so precise and so reliable that in some ways we're sort of the gold standard, and it's hard to argue with our result. And so they can calibrate the performance of their instruments against ours.
What do you see as the future for similar small-scale Canadian missions like this?
Oh, I think they're the wave of the future, and the Canadian Space Agency knows this. They've got 2 or 3 more like ACE in the works, and it's a way a small country like Canada can make a big impact without spending, $1 billion and shipping up a satellite the size of a school bus. We build the instruments in Canada. Of course, we still have to buy a launch, but the world is awash with launch opportunities.
Proving once again that small really is beautiful.
Couldn't agree more.
Dr. Bernath, thank you very much.
Thank you, Bob.
Dr. Peter Bernath is a professor of chemistry at the University of Waterloo and the ACE mission scientist. Coming up next, burping the baby Earth.